Yeah, so we're talking about amplitude modulation. Modulation of two signals is simply signals multiplied together. And in the case where we have maybe two sinusoids where one has a much higher frequency than the other one, like that, the resulting waveform becomes contained within the envelope of the slower one. So the resulting waveform becomes something like this. That is, the carrier becomes modulated by the modulator. And the expression for this is the modulator with the frequency times the amplitude with the carrier and the carrier frequency like that. And this is a simple form of modulation, of amplitude modulation, I can say. Okay? So this is what it looks like in the time domain. Very naughty me, forgot the time there. The envelope is fluctuating like this. If you're playing an instrument like tuning guitars and other string instrument, usually you try to find frequencies that are exact between the two strings. And when you're looking to find that exact frequency, you sometimes will hear not different tones when they're really close, but the fluctuation in amplitude. So there's a modulation between the two strings that are affecting each other. So these beat notes is a type of amplitude modulation, if you heard that before. When we talk about frequencies, what would this look like in the frequency domain? Well, to make this simple, let's just say that AM equals AC, and that they're both 1. So we have cos omega C, and I'm going to skip this one as well, times cos omega M. Now, if you know your trigonometric identities, there's a very handy expression that says that cos x times cos y equals half cos x plus y and cos x minus y. So already from there, we know already what's going to be in the frequency domain, don't we? We know that of the frequencies we have a carrier frequency which is usually higher than the modulator, which can be down here maybe. And the resulting frequency spectrum will be then cos omega C plus omega M plus cos omega C minus omega M. So centered around the carrier frequency, but at a distance that is equal to the modulator frequency, we will have two components, and there will be half the amplitude. And this distance, you can call this delta F, or you can call it, in this case, it's actually the distance is the frequency distance there is the same as the modulation. So we have a carrier that is not actually present in the spectrum anymore, and 2 side bands. So what happened to the carrier? It sort of disappeared, right, in the modulation. We can add it together. So the expression for real amplitude modulation with the carrier present is actually 1 plus A carrier cos omega t times and the modulator. This is the amplitude modulation with the carrier present. Then the carrier will show up in the spectrum. Otherwise, as in this case, it's called ring modulation, and the carrier will disappear from the resulting signal.